All right, hi there. Let's continue on with chapter 2. Um, and chapter 2 is about atomic structure and periodicity. Now, atomic structure, the modern atom that we're going to be talking about, is based on quantum mechanics. So, really, this chapter is going to teach you all about the quantum mechanical uh, model and how that came about. So before we do that, we got to talk about radiation, okay? And this isn't the radiation that we talked about when we were talking about Ernest Rutherford and Henri Becquerel. This is electromagnetic radiation. Now, electromagnetic radiation is uh, how energy propagates through space, okay? And it does this by having an oscillating magnetic and electric field, okay? Uh, and I will show you what that looks like. But the thing is, we characterize anything that's electromagnetic radiation following um, four-ish um, uh, properties. Okay, so the first property is going to be that of wavelength. Okay, wavelength is the distance between the two crests of adjoining waves, or two troughs of the wave, or actually any 2 points on adjacent waves. Now, wavelength gets a Greek letter lambda. Okay, the Greek letter lambda. So I'll show you how I draw it. It's just kind of like uh, a little hat on top of a line. That is wavelength. Now, oftentimes wavelength is given in nanometers. Okay, 10 to the minus 9 meters. So keep that in mind um, as we're going through these calculations, that we need to make sure that we stay in the SI unit system. So wavelength is oftentimes going to have to be in meters. Okay, and then the second is frequency. Now, that may look like a V, but it's actually the Greek letter nu. Okay, frequency is the number of waves traveling by a given point over time. So it's number per second. Um, so the units of frequency are inverse seconds. So seconds to the minus 1, or they get a special unit called the hertz. Okay, Hz. You may have heard of hertz, megahertz, or kilohertz on your radio dial, and that's what they're talking about. Now, that Greek letter nu actually kind of looks like what you would, seagulls in a painting. Um, so that's how I draw a nu. Then the third thing we're going to be talking about is speed. Now, all electromagnetic radiation travels at the exact same speed, and that is the speed of light, which is 2.9979 times 10 to the 8th meters per second. Or, for a lot of different books, we often call this 3.00 times 10 to the 8th meters per second. Now, because speed is given in meters, we need to make sure that whenever we have a wavelength, we get it into that meter unit system. Now, the relationship between wavelength and frequency is an inverse one, okay? In other words, as one goes up, the other must go down. So lambda is proportional to 1 over wavelength. And if you think about it, wavelength is a length, and frequency is number of waves per second, or inverse seconds. If you multiply wavelength and frequency together, you get a speed, and that is the speed of light. So lambda nu is equal to c. So as you can see on this slide, the nature of waves. Now, if we've got a graph where 1 second is that long, okay, um, what we can see is the relationship between frequency and wavelength. So here the frequency in this red line is 4 cycles per second, or 4 hertz. That's because you've got 1, 2, 3, and then 4 total waves passing by during 1 second. And that's given lambda 1. Now, lambda 2, which is shorter than lambda 1, Okay, for the green wave, you can see this is 8 cycles per second, or 8 hertz. Lambda 2 is going to be shorter. And then in the blue, you can see 16, lambda 3 gets even smaller. So as frequency goes up, wavelength goes down. Okay, as wavelength goes up, frequency goes down. Okay, inverse relationship. Now, I had talked about what electromagnetic radiation was, that it was an electric field and a magnetic field. And I think this is actually kind of an important thing to notice, okay? So if I've got a wave propagating through space, okay, it's going to have both an electric and a magnetic component. So the electric field is going to be, let's say it's going to look like a sine wave traveling in that direction, okay? Now, the magnetic field, remember electricity and magnetism, two sides of the same coin. The magnetic field is going to travel, but it's not going to be in the same plane as the electric field. The magnetic field and the electric field are actually 90 degrees from each other. That's what we call, they're normal to each other. So what we would see is and forgive my fact that I cannot draw very well, this guy be in the flat plane here, okay? Such that, well, if I could draw better, you might see it easier. Such that the two components are perpendicular to each other, okay? And because there is an electric component and a magnetic component, we actually can bend light with a big enough field. And this is actually how we've determined a lot of things astrophysically by the movement of light. Okay, we can actually speed light up and slow it down. All sorts of cool things that happen with this. But for us right now, the important thing is that light can behave like a wave. Okay, and that we use these wave terms in order to characterize light. Okay. Now, electromagnetic radiation falls on a spectrum, okay, and hence what we call the electromagnetic spectrum or the electromagnetic radiation. So we're going to take a look at this in terms of wavelength and frequency. So at the really, really tiny wavelengths, 10 to the minus 2, 10 to the minus 12, sorry, we have the things called gamma rays. Now, gamma rays we talked about as being part of the radiation from the atom, right? Remember alpha, beta, and gamma? I said back then that gamma rays were high energy light, bits of light, and that's what we have here. They've got a really, really tiny, tiny wavelength, but a really, really high frequency, okay? Gamma rays actually are used in sterilization of food products. It's actually kind of neat that if you take an apple that has been subject to gamma irradiation and one that hasn't, and you just let them sit around, the gamma irradiated apple will not rot for a very long time because rotting is a chemical process brought on by bacteria. The gamma radiation can kill all the bacteria. And before you start freaking out thinking that your apple is radioactive, the gamma rays don't stick around. It doesn't stay in the apple. Okay, all it does is it passes through and kills all the bacteria that would cause it to spoil. Okay, it's kind of neat, but people kind of freak out about it. But it's really a very useful technique in food preservation for long periods of time. All right, moving on up, we hit the X-rays, about 10 to the minus 10 meters. Okay, so 1/10 of a nanometer. Okay, or yeah. So X-rays, well, we know what X-rays do, right? We can use them to image the human body. I don't think I need to say much more than that. Everybody knows what an X-ray is. Then we hit the ultraviolet, about 10 to the minus 8, going into the 10 to the minus 7 range. Ultraviolet is the section of the spectrum that allows us to tan. It is also the one that gives us skin cancer. But what's kind of neat is there are a lot of animals that actually see in different regions of the electromagnetic spectrum. So ultraviolet is one of those regions where bees actually can see in the ultraviolet. And what they see when they take a look at a flower is not what we normally see. It's actually really kind of neat that if we take a UV photograph of a flower, a lot of times it looks like a gigantic bullseye for the bee to home in to where the pollen is. It's really kind of neat. And when we get together, I will definitely show some pictures. Another interesting one is parrots. Parrots see in the ultraviolet. And when you shine on ultraviolet light on a parrot, it is way cooler than just seeing a normal parrot. Anyway, so I digress. Moving on from about 400 nanometers to about 700 nanometers, we have what we call the visible range. Now, the visible range is all the range of wavelengths that we think of as color. So, what are the colors of the rainbow? Roy G. Biff. Okay, red, orange, yellow, green, blue, indigo, and violet. Blue is at the low short wavelength end, the high frequency, and red is at the low frequency, longer wavelength. After visible, we hit the infrared. Now, wait, let me just tell you, this should be a range of numbers that you understand. 400 to 700 nanometers, you need to know that that's what humans classify as the visible. Okay, so you need to know that range. So moving on, a little bit further down the range, we hit the infrared. Infrared is what we feel as heat as human beings, and following along the animals seeing different colors, pit vipers tend to sense infrared. Kind of neat. But when you feel the sun warming you up, it's actually the infrared radiation that you're feeling. Now, moving even further on, we hit microwaves at about 10 to the minus 2 meters. Microwaves, obviously, we use to cook our food. But there's a lot of other interesting uses for microwaves. Communications, big one. Satellite communications are often use microwaves. A second one that's a little less known is crowd control, which is kind of cool because if you have a riot going on, and most riots have a few key agitators, people who really stir up the problem. And what they do is they take this microwave gun and they aim it at the person who is really stirring up the thing. And what ends up happening is it starts to interact with the water molecules in their body and heating them up. And basically, I don't know about you, but I've never felt like rioting when I had a fever. When they start to warm up, they start to feel kind of sluggish and don't feel very good. They tend to stop rioting. So, kind of a neat little thing for microwaves. Then we hit the radio waves. Now, radio waves tend to have really long wavelengths, on the order of meters or kilometers. So radio waves, things like car radio or TV or cell phone, these fall into that radio wave category. All right. So I would know, if it were me, I would know the general trend here: gamma X, ultra visible, infrared, microwave, radio. And I would definitely know 400 to 700 nanometers is considered the visible range. All right. So there is some math when dealing with these electromagnetic radiations. So here we have an example problem. The brilliant red color seen in fireworks are due to the emission of light with wavelengths around 650 nanometers. And this comes when you have things like strontium salts. being heated. So the question is, calculate the frequency of red light if we've got a wavelength of 650 nanometers, or 6.50 times 10 to the second nanometers. All right, so we're going to calculate the frequency using the speed of light. Lambda nu is equal to c. So lambda nu equals c. Rearrange that, we get nu is equal to c over lambda. Now the key here is to make sure that you have your units in the right size. We are given nanometers, so we need to convert the nanometers into meters. And remember, 10 to the 9th nanometers is 1 meter, okay? So you could have just moved the decimal place 9 spots and gotten 6.50 times 10 to the minus 7 meters, okay? So putting in our value for the speed of light and our value for the wavelength, 2.9979 times 10 to the 8th meters per second over 650 times 6.50 times 10 to the minus 7 meters, gives us 461, or 4.61 times 10 to the 14th inverse seconds, or 4.61 times 10 to the 14th hertz. Okay? Now, I would really suggest that you continue to work on problems like these. These are the simplest type of problems. When I either make another video or see again, we'll work on some of the harder problems. Okay? All right. So, to give you kind of an interesting little use of this, if you actually apply current to a pickle, it will glow orange, okay? And the reason for this is because there's salt in a pickle, okay? Sodium chloride. And when you get enough energy into those sodium atoms, okay, they start to get excited. They get excited kind of like a little kid on candy, okay? When little kids get a lot of candy, they start jumping around, giving on, high energy. And what eventually happens is they expend all of their energy and then they crash, right? They hit what we call the ground state, okay? So they've expended all their energy and then they crash. This is the atoms getting a whole bunch of energy and then they crash. They give it all away. And that is the light that we see. And it is a yellowy orange because primarily sodium. So next time you're walking through a parking lot and they've got those really weird yellowish lamps going on, think, those are sodium lamps because of that yellow color. Or next time, if you've ever cooked boiled water and it's boiled over on an open flame, you get that nice yellow color. That's sodium. Okay. So, and this is the end of section 2.1. Hopefully, I will see you guys soon. And if not, I will make another video and we will talk about it then. Have a good one.